It's your man Bruce Wildenmuth here and Edward Klein, and we did our presentation on Newton's laws. Let's do this. Alright, we're going to introduce the man himself, Sir Isaac Newton. He was born January 4th, 1643 in Colsterworth, United Kingdom. He went to school at Trinity College in Cambridge and was an English physicist and mathematician who excelled in calculus, which he contributed a lot to the math world, physics world, and scientific revolution. He was a big guy, helped with a lot of stuff. Alright, so Newton's first law. Newton's first law states that an object in motion stays in motion with the same speed in the same direction, unless acted upon by an unbalanced force. Looking at that picture there, which is forces balanced, you see that objects at rest with a zero velocity, with zero acceleration, stay at rest. They don't want to move anymore. If they're sitting on a table, it does not want to move. That's why it's going to stay there and not jump off the table randomly. And objects in motion with a non-zero velocity and a zero acceleration are going to stay in motion. They're just going to keep continuing the same speed and direction a certain way unless another force, unbalanced force is acting upon it, such as friction to slow it down or something. So if we go head over to this Fed over here, we can see that we have no friction, and we got a box and a guy, and we're going to apply 50 newtons to the left, and then we're going to take it off. We're going to keep the speed on. You can see that the speed is not going to want to change at all, because an object in motion wants to stay in motion, so it's not going to just going to keep moving. But yeah, so it's going to keep going. So then we're going to go back over to here, and we're going to go to Newton's second law here. So Newton's second law states that objects that are not balanced, it says that acceleration is dependent on the object's mass and the force acting on it. Therefore, as the force is increased, the acceleration of the object is increased. And as the mass of an object is increased, the acceleration of the object is decreased. Which the equation is derived for this law, which is F equals ma, or A equals F divided by m. And the Newton is 1 kilogram times meters per second squared. So if forces are unbalanced, there is an acceleration. And the acceleration depends directly upon the net force, or the acceleration depends inversely upon the object's mass. So that is stating that if we were to just let this keep going, say it's at the same time, if we act an unbalanced force in the opposite direction, it's going to change it completely. It's going to make it go the opposite direction in a different way. So, and then if we keep it there, no friction, nothing, it's going to stay at rest. It's not just going to move on its own, because it does not want to. It doesn't have the energy nor force to move on its own to overcome that static friction. Alright, now we're going to move on over to Newton's third law here. And Newton's third law states that for every action there is an equal and opposite reaction. This means that, well, if I punch a wall, the force I apply to the wall is equal to the force that the wall exerts on my hand. Same thing with that picture there, with the force of a finger on the wall is directly the same as the force of the wall on the finger, because they can't create any more force than they already have together. So it's just going to stay at the same. Same thing with the if a bug flies straight into a windshield of a car, which one exerts a greater force? It's going to be the car. It's going to be the same. It's going to be the same because they both exert the same amount of force because of Newton's third law. And yeah. Alright, it's your man Brucey B out here at Old Iron Keep here to show you some new physics. So what we're going to show is that objects with more mass exert a greater force following Newton's second law, that F equals ma, mass times acceleration equals force. So we'll say if I use this great hammer, which weighs roughly 26 kilograms, and we'll compare it to, let's say a club. We'll say a club that weighs only 3 kilograms. We'll put that there. So then, if we walk over to this kind fellow over here, is going to be our demonstrator for today, and we just flatten him. He exerts so much force it knocks him off his feet. So we're going to run over here. We're going to give him a little break. We got to give the crew member a little rest. So we saw that because this weapon was 8 kilograms, We're going to multiply that times the acceleration of the swing, which we can't calculate really. But it's going to be a lot of force coming down on. That's why I knock him down. And we just go straight to the club, which is a lot smaller, doesn't have as much mass when we hit him. It's not going to knock him over. It is going to stagger him, but it won't knock him over. It's not great enough force at all, really, to even knock him down. And if we use something even smaller, we'll say a small dagger. It's not going to knock. It shouldn't even come close to even staggering him or knocking him back at all. Just because F equals ma, mass times acceleration. The heavier an object is, the more force it has behind it to knock something back or to knock them down. So we'll say, yeah, it's just keep knocking them back. It's not even doing anything. But then if we show more mass, flat. Alright, yeah, that's it. That's the end of the video.